Learning Boolean algebra by designing a reduced and full binary to hexadecimal 7-segment decoder using negative and positive logic techniques. First we'll look at the complement law proof using an OR gate where A or not A equals 1. So we've got an OR gate and the inputs to it are A and not A, and one of those is always going to be 1. When A is on, not A is off. When A is off, not A is on. So one of them is always on, so the output is always true. So A or not A is always logic 1. Proving the absorption law using logic gates and a truth table where A or not AB is the same as A or B. So we've got the circuit for A or not AB, and we've got the inputs A and B which count from 0 to 3 or 0, 0 to 1, 1. We have an AND gate for the not A ANDed with B, and we have an OR gate for A ORed with not A and B, and we want to prove that that column is the same as A or B, which would be 0, 1, 1, 1, where the OR function is true if either input is true. So when both inputs are low, not A ANDed to B is low, so the OR gate output is low as well, because the OR gate has no inputs that are high, so it needs one of them to be high for the output to be high. So far A or not AB is the same as A or B, but we need to prove it for every case. So when the inputs are 0 and 1, A is high, so the output goes high through the OR gate, but not A and B is low, but that doesn't matter because A or not A and B is high. And that follows what an OR gate would do, a 2-input OR gate. So far they're true. The third case where B is high and A is low, not A ANDed with B goes high now. So the OR gate has one logic 1 signal on its input, so the output is high. So far A or not AB is the same as A or B, but we need to prove it for every case. Now both inputs are high, and so long as A is high, the output will be high through the OR gate. So this proves that the two expressions are the same and can be interchanged. A or not AB is the same as A or B, so we're saving ourselves some logic gates. And this is just a quick animation to go through the truth table a few times. We can have multiple ANDed variables in the second term, and only the single complemented variable disappears. So if Q is A or not ABC, that's the same as A or BC. So it doesn't matter how many terms are ANDed in the second term, only the complemented one disappears, and we'll talk more about that in a second. So the absorption law is really getting rid of the imposter, a complemented variable that doesn't belong among the other ANDed terms. So A or not ABC, the not A is the complement of the A, which was the single term, so we need to get rid of it. Not X or X, Y, Z. Not X was quite happy on its own, but it has its imposter in the ANDed term, the X. So we get rid of X, so the function is not X or YZ. Not B or ABCD. The not B was quite happy as it was, but then it was had its imposter in the ANDed term, so we need to get rid of the B, so that's equal to not B or ACD. Similarly, B or A ANDed with not B and C and D, the not B is the imposter, so we get rid of that. Not A, C, E or A. Well, the not A is in the ANDed term, and it's the complement of A, so we need to get rid of not A. So that's equal to C, E or A, but I write that alphabetically, so that's A or C and E. A ANDed with not C ANDed with E, or C? Well, the not C is the imposter here because it's in the ANDed term and it's the complement of the single variable. So we get rid of the not C. This is equal to C or A and E. Next we have not F, A, C, E or F. Well, the not F is the complement of the single variable, so this becomes A and C and E or F. And at the bottom, F, A, C, E or not F. The not F was happy on its own, so the F is the imposter and needs to be got rid of. So always get rid of the imposter. You may get an expression written down that's not in alphabetical order, so it's worth writing them in alphabetical order first. So we have A and F and D and B and C and E, or not B. Well, the not B was happy on its own and it has its imposter in the ANDed term, which is the B. So we get rid of the B term. So this is equal to not B or A, C, D, E, F when written alphabetically. And I'd recommend always writing them alphabetically unless you forget, because it's much easier to compare the different expressions when they're written like that. So that is the absorption law. Now we're going to design the part hexadecimal decoder whilst using Boolean algebra simplification techniques with positive logic expressions for when the output is true. So here we have a table of binary inputs, the decimal equivalent number and the hexadecimal equivalent number, and we've got a table of 7 segment displays. They're labelled A to G, going clockwise around from the top and then in the middle. So our DCBA inputs, they're actually outputs from a 4-bit counter, and they count from 0000 up to 1111, which is 0 to 15, which is 0 to F in hex. So what we are going to do, because we're only interested in making a part hex decoder for when the hexadecimal numbers are A to F, we need to make sure that all of the segments of the 7-segment display are turned off until we reach count 10 or A in hexadecimal. So all these are low, and our design kicks in when we get to the decimal number 10 or binary 1010 or hexadecimal A, and that's when we're going to start designing to turn the segments on to represent the letters of the hex number. So this is the part of the truth table that we're interested in. Everything else has been 0 to this point on the output segments. So we're interested in from A to F, and we're using capital A, E and F, and we're using lowercase b, c and d so that it doesn't look like 8 and 0 for D, and we're using the small c at the bottom, and we're going to figure out when the segments are lit up, or logic 1, depending on what the hexadecimal character is that we want to show. For the decimal number 10, which is hexadecimal capital A, the segments that are lit, all of them apart from segment D. So the truth table shows which segments are turned on to show the capital A hexadecimal character, which is equivalent to 1010 in binary, which is 10 in decimal. So all of them are lit apart from the bottom one, segment D. For decimal number 11, which is B in hex, we're using a lowercase b so that it doesn't look like an 8, and the segments that are lit are C, D, E, F and G. So the only ones that are switched off are segments A and B. So we're building up our truth table. Then for decimal 12 or hexadecimal C, I've chosen the little c rather than doing a bigger one, and D, E and G are lit up. All the others are at logic 0. Then for 13, which is D, the only ones that are switched off are segments A and F. To represent 14 or E in hexadecimal, they're all turned on apart from segments B and C. And then for segment F, we've got A, E F and G lit, and the others are at logic 0. So if we look at wiring up our segments to our Boolean expressions which are going to be implemented in logic, we need to figure out what logic gates to use. So segment A, we'll look at it segment by segment now. A is high at these three cases highlighted on the left. So we make Boolean expressions for these and then use those logic gates to wire up to segment A. So that's D not C, B and not A. Then DCB and not A. Or DCBA, so that's D and C and B and A. But if you notice, the second two terms have DC and B in common, multiplied by not A or A, which is the complement law. So we rewrite it, take out the common factors of the second terms, DCB brackets not A or A, which is the complement law. And not A or A is equal to 1. So really this simplifies down to D not C, B not A, or DCB. The bottom two terms both have D and B as a common factor, and then we use the absorption law, C or not CA, to simplify down. So we've started off with the top and now we've simplified to two AND gates and an OR gate for segment A. So using multisim or Proteus or something like that, we will implement this logic from our binary counter, and that will make segment A light up when it's meant to. Now for segment B, that's only lit up twice in the numbers that we're interested in. And the Boolean expressions for those two cases are D not C, B not A, or DC not B A. But this cannot be simplified because although they have D in common, everything else is changing. There's too many changes to use the complement law or the absorption law. So we will implement this using the logic shown. For segment C, it's high for three different states, and they are D not C, B not A, or D and not C and B and A, or DC not B A. Look for some similarities and differences. So we've got D not C B as a common factor in the first two terms. So this is the complement law, where the not A or A is redundant. So these two bottom terms have D in common, but the C changes and B changes. So there's nothing else we can do. There's too many changes to implement the complement law anymore or the absorption law. So we just wire it up from segment C using these gates and the Boolean inputs from the counter that we're going to make. Segment D, it's active for four different states. So the Boolean expressions are D not C, B A, or D, C not B, not A, or DC not B A, or DCB not A. So we're looking for similarities and differences. If you look in the second and third terms, they both have DC not B as a common factor. So we're going to use the complement law to get rid of the not A or A, which is equal to 1. So this just becomes D not C, B A, or DC not B. And then don't forget the last term, DCB not A. But then the second and third terms have DC in common, and not B or B not A. So that is the absorption law for the second terms. So it's the B that is taken out by the absorption law. So we've got rid of one variable in one of the terms, and then we just write out what is left. So this is how we will implement that using 3 AND gates and an OR gate. Segment E is always high, but we can't say E equals 1, otherwise it'll always be on from the start of the count. And you'll also notice that segments E and G are the same value, so the Boolean expression for E is the same as for G. And we just write down the terms from our truth table. There's 6 of them, and we look for similarities and differences as we go along. You can see terms 3 and 4 have stuff in common, and terms 5 and 6 have things in common. They're the 6 expressions for the states when E and G are high. So the first 2, it's the A that's redundant using the complement law. The second 2 is the same thing, and the third pair also have common factors. So we can use the complement law 3 times here. D not C B multiplied by not A or A, DC not B into not A or A, and DCB multiplied by not A or A. And remember, a complement odd with its variable is equal to 1. But you'll notice even once we've simplified, the first and third terms have D and B in common, and C or not C is 1. So we can further simplify with the complement law. So E is just equal to DB or DC not B. But they each have D in common, and then it's the absorption law, B or not BC. Take out common factors and then simplify the bracket and then multiply out again like normal algebra. So we're just going to wire our logic gates from the counter through these 2 AND gates, and we're going to wire it to segment E and segment G. So we've saved ourselves loads of logic gates, and that's why we do this, to make our circuits more efficient and smaller and less complicated. Finally, we're going to look at segment F. So that is high for 4 different states. So we'll say F equals D not C B not A, or the second one, D not C B A. So there's the complement law. DCB not A and DCBA. So the complement law again. So we've got D not C B as a common factor into A or not A, and the same with the other 2 terms, DCB as a common factor. So this will become D not CB or DCB. But even then they both have D and B in common, with not C or C as the other term. So again, the complement law, segment F is just equal to D ANDed with B, a simple 2-input AND gate. So we've fully designed our part hexadecimal decoder. Now we're going to implement it. So creating the binary counter, making the binary outputs DCBA and their complements, and implementing the circuit. So using Proteus or multisim or symmetrics, I'm using Proteus because I prefer it. I'm going to click on the components mode and search for 7474 D flip-flop to make our counter. Then I'm going to type logic state and get one of those. I'm going to get a logic probe to look at logic levels. I'm going to get a ground. So click on terminals and ground. That'll be for my 7-segment display, although I forgot what I needed it for a minute. And then generator mode, a digital clock to drive the 4-bit counter. Then back to devices, click on 7474 and quickly build a 4-bit ripple counter. Just trying to line it up nicely. The not Q outputs go into the data input, and the not Q outputs also clock the next flip-flop. So this is a ripple or asynchronous 4-bit counter just to provide a timing signal for our count. Wire up the clocks and clock signals between the flip-flops. I'm going to get some logic probes to see what the logic levels of the clock are and the Q outputs. So the Q output from the first flip-flop is our binary A variable. Then the second flip-flop gives us our B variable. C comes from flip-flop 3 and the binary variable D comes from flip-flop 4. You may want to watch this part of the video in like times 1.5 or times 2 speed. You may be familiar with counters already, but I'm trying to make the video as detailed as I can without it being too long, but feel free to play it a bit faster. But after I've got the logic probes, I'm going to double click the clock. It's at 1 Hertz. I'm putting it at 2 to make it a little bit faster. And you can see it counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and then back to 0. And it'll do that indefinitely. So now I'm clicking on junction mode just to make some wires for outputs A, B, C, D and not A, not B, not C, not D, just so we can tap off from them with our logic gates. So it's kind of like having a bus for all of the Q and not Q outputs. Remember, the not Q outputs are the complement of the Q outputs, so they serve as our not A, not B, not C and not D variables from flip-flops 1 to 4 respectively. So I'm wiring up output B, then output C, then output D. Whoops, done it again. So there's output D, and then from the not Q outputs we get our not A. I'm doing not A now. Then not B. Make sure it comes from the not Q output, don't get confused or nothing will work properly. Then not C, so that's the not Q output of the third flip-flop. And then finally not D. Proteus is a bit annoying with the wiring sometimes, so if you click you can make an anchor. So there's the not Q output of the fourth flip-flop, which is not D variable. Then what I want to do, I'm going to grab or lasso around them. I'm going to try and pull them and make them longer. And I did that. Now I'm going to make them a bit thicker and change the colours of them. So I'm going to use like snooker colours white, yellow, green, brown. So in my mind, I know what order they are. So I'll right click the wire, edit wire style. You can change the color if you uncheck follow global. I end up making them thicker as well in a minute. Edit wire style. So that'll be yellow. So it goes white, yellow, green, brown, like the snooker. So you can change the width. I'll make it 66th. And then do the same for all the others. And I'm going to make the complement wires. I'll put them next to the main wire, but so that I don't confuse them. I fast forwarded a bit and I've added a 7-segment display. And now really we're ready to wire up our first expression for segment 8, which was dBc or dB not A, or DCB or dB not A. So I need 2 3-input AND gates and a 2-input OR gate. So I'll wire it to D, which is the 4th flip-flop, and B and C, and I also wire D, B and not A. But I've even made a mistake here, which I'll rectify later. I just want to show you the effect of having the wrong wires. But it's generally right, but I made a small mistake, which I'll rectify on my logic. I need a ground for the 7-segment display. And I wired that logic into segment A for that expression. Now we're going to do segment B, which was 2 4-term AND expressions and an OR gate, because it was D not C, B not A, or DC not B A. So we'll wire that up. I've added some text labels. The little capital A on the left hand toolbar, just click that, and I added some text for the wires. So D not C, B not A, so that's correct. And then DC not B, if I do that right, and A. And then I'll wire the output to segment B, because this is the Boolean expression for segment B. Then for segment C, has 3 terms ANDed and 4 terms ANDed, so we need a 3-input AND, a 4-input AND an OR gate as well. Now because segment C's Boolean expression was D not C B or DC not BA, I could have tapped off the DC not BA from segment B. But I'm just showing you how to do it fully, and we can optimize at another time if we want. So this is segment C of the 7-segment display, and we have D not C, B or DC not B A. So we're just wiring up to make our Boolean expressions. Then on to segment D. That was a 4-input and a 3-input and another 3-input AND gate, and we need a 3-input OR gate. So I actually did this incorrect just to show you the effect of having the wrong logic. But anyway, it outputs to segment D, and then we do a little bit of testing, and then we figure out where our errors were. So even though you may wire them wrong sometimes, it's a good teaching experience to figure out how to fix it and how to identify which expressions are wrong. So I've done segment D with the wrong logic here, but nevertheless I've wired it up to segment D. And then for segment E, which is also segment G. It's just two input AND gates and a 2 input OR gate, because the expression for E, which was also the expression for G segment, was dB or DC. So we'll just wire that up. We'll put the output to 2 places now. So this is going to be D and B, ORed with D and C. So that's that. Wire the output to segment E, but we're also going to wire it to segment G because they have the same Boolean expression. So that's segment E. Then I take a wire from segment G, the last segment, and just connect to E. And then finally, segment F, which the expression is D and B, we've already made D and B for segments E and G. So what we can do is get a junction and put it on the output of D and B, and then just take a wire off it. We don't need another gate doing the same thing. And then that goes to segment F. So wire it there and we're good to go, but we do have a few errors that I put in. So it counts from 0 and 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So there are some errors. 7, 8, 9, A, B, C, D, E, and we have E again. So the segments that are wrong are segments A and segment D. But we knew segment D was wrong because I'd put the wrong logic in. So we just need to verify what it should have been and then implement that. So check your Boolean expressions, always have them written down to make sure that you're putting the right gates in. It's so easy to get confused. So the expression that I should have had for D was a 4 input AND gate and 2 3 input AND gates. And I replaced the 2 input OR with a 3 input OR. So the expression should be D not C, B A. So that is correct. And the other expressions were DC not B and DC not A. So I've got DC and not B there, and then I just need D, C and not A. I could have tapped the D off the other gate, but just to be clear, it's always best to take them from the original bus if you like. DC and not A. So that'll fix segment D. We'll identify that shortly if there's a problem with segment A. So we'll simulate it again and see what it looks like now. 1, 2, 3, 4, 5, 6, 7, 8, 9. A isn't quite right still. So where it says A, segment A is missing, and where it should say C, there's an extra segment. That's A, which is worth 10. So the top segment A should be lit and it's off. So we know there's something wrong with it. And if I just go through a bit more, B's okay by luck. But again, where it should say C for hexadecimal 12, that's wrong. But if you look at the expression for A, it should have been DCB or DB not A. But I've got DCB or DC not A. So always be really careful when you're wiring up your logic that it comes from the right output. Now it should work. 4, 5, 6, 7, 8. A, B, C, D, E, F. So we've done it, we've cracked it. We've made and designed a part 7-segment display hexadecimal decoder for the characters A to F. Now we're going to design a full binary to hexadecimal decoder using Boolean algebra and using negative logic. So we're looking for when the output is low because it's often more efficient and quick. So this table shows us when the segments are lit or not lit for all counts from 0 to 15. And we're going to use negative logic. We're going to focus on when the outputs are low because there's less cases to deal with and less Boolean expressions. So for not A is these 5 states, whereas there was loads more when A was high. So we can find the expression for not A and put it through a NOT gate and get the expression for A. So the first state when it's low was not D, not C, not B, A, or not D, C, not B, not A. And we just go through the table making Boolean terms to find a Boolean expression for not A. And I'll show you how to wire it up. So that's the last case when it's low. And the last 2 terms have common factors of DC not B. So that's the complement law in terms 4 and 5 there, where the value of A doesn't matter, so it's redundant, so we can get rid of it. So that's DC not B as a common factor, term 4 as not A, term 5 as A. So that means it doesn't matter whether A is high or low. So it's redundant, so the complement law gets rid of it. So then we just write it out again. So it's going to be or DC not B. And then we're always looking for similarities and differences. The second and fourth terms now both have not B and C as a common factor. So we have D or not D, not A, which is the absorption law. So those two, if I want to see what they're worth, we have the common factor of not BC, or we could have said C not B. And then the other terms are D or not D, not A. And remember the absorption law, A or not AB is A or B, so you get rid of the complemented variable in the AND term. So those 2 terms are worth B not C into D or not A, which is not BC D or not BC not A. So then we regroup and write what we have for the overall expression not A. The first term, not D, not C, not B, A, or the equivalent of these 2 that we use the absorption law on. Write those down. D not C, B, I'm doing it in alphabetical order usually. So there's the expression for not A, and we're going to tap off from the counter logic like before. And instead of using an OR gate, which gives us not A, we could use a NOT gate after to give us segment A. But an OR gate followed by a NOT gate is a NOR gate. So we can use negative logic with a NOR gate to get the correct output. Now we're looking at when B is low because there's less cases than when it's high. So not B is those 1, 2, 3, 4, 5, 6 cases. So write down the Boolean expressions. The fourth one is DC not B, not A. The fifth one, DCB not A, and then DCB A. So you can see the complement law in the last 2 at least. I'll number them, make it a bit easier to keep track. So in terms 2 and 5, we've got B and not A and C as common factors. So it's the D that we apply the complement law to. So we have CB not A multiplied by 1, because that's D or not D. So write out the expressions again with any changes that we've made. Get rid of those two terms and replace them with the overall output that we created with the complement law. And then write down any existing terms. And look at those for similarities and differences. So terms 3 and 5, we have common factors of dB and A. So it's the C that's a redundant term from the complement law. Then clean it up again. Those two terms gave us dBA. But you only need to write D and B and A once. Label them again. The second and fourth terms, can you see anything? We've got C and not A in both terms. So they'll be the common factors outside the brackets. So that is the absorption law. In the bracket is B or not BD. So that not B is going to disappear. So we end up with C not A into B or D. So that's C not A B or C not A D, which you can write in alphabetical order if you want to. So we've used the absorption law, CB not A or DC not A. So we'll cross them off, use the two that came as the output from the absorption law and regroup. So not B is equal to not D, C, not BA, or we already had dBA, or the two terms that we just came up with from the absorption law, CB not A or DC not A. I usually cross them off as I've written them down so I don't duplicate and bring things back into the expression. And that is it for not B, because we don't have enough differences or similarities to use any more laws. So we're going to put those through a NOR gate and give us segment B. Now for the expression for not C, because there's only 4 cases when C is low, so we should focus on those instead of all the other cases when it's high. So that is negative logic. So we've got not D, not C, B not A, or DC not B not A, or DCB not A, or DCBA. So immediately we can see the complement law in the last two terms. So I'll highlight them, number them. So terms 3 and 4, complement law, because they both have DCB and they have A or not A. So the value of A doesn't matter because both terms are true. So A is redundant through the complement law. So just write out again what we have now, or DCB. So what are the commonalities here? So we've got the last two terms. We've got DC as common factors. Then we've got B or not B, not A. So that is the absorption law. So bring out the common factors. D and C into not B, not A on the second term, and just B on the third. But because the complement is in the ANDed term, we get rid of not B and then multiply out. So that's going to become DC into not A or B, multiply out, DC not A or DC and B. So C is equal to not D, not C, B not A, or those other two terms. And there's no further simplification that we can do. So that is the output for not C. Put it through a NOR gate and it gives us the output for segment C. Because if you have odd terms and then they are negated or complemented, that's going to give us a NOR gate to give us the output for C. Now to find the expression for not D, because there's only 6 out of the 16 cases where it's low, we'll use negative logic. You can flip between positive and negative depending on how many terms that you have to deal with. I'll just write down the Boolean expressions for these 6 terms. The last one is DCB, A all ANDed. So numbered them, terms 1 and 4. Do you notice anything about them? Not C, not B, A in both terms. So the value of D is irrelevant to those two terms being true, so the complement law gets rid of them. So we have not C, not B, and A, which accounts for terms 1 and 4. Then we write the others down where they were, so we don't forget about them. We're always looking for similarities and differences, so these two terms, again, it's the complement law, where the value of D is irrelevant. So they both turn into C and B and A, or CBA. Or CBA, get rid of those two, or whatever was there before. And now for output not E, we've got 1, 2, 3, 4, 6 different states when segment E is low or not E is true. Write down what they are. So we're just looking at the binary values on the from the counter, and the last one, D not C not B, A. So we're looking for similarities and differences. You spotted any? So terms 1 to 6, it's good to label them so we can refer to them. Terms 1 and 2 are the same, apart from one of the variables. So they have a common factor of not D, not C, and A, and it's the B that's redundant in those two. And then we continue looking for more. Terms 3 and 4 have D, C, not B in both terms. So it's the A level, logic level, that's irrelevant. So the complement law knocks out the A term in that one. Now with this term and the third term, they have not D and A in common. Then we have not C or CB. So that is the absorption law. Not DA is common to both. We have not C or CB. So it's the C that we get rid of with the absorption law. So then we just multiply out to what's left. So not E is equal to the first term, not D, not CA, or the other part of the absorption. What we had anyway, not D, C, not B, and the last term, D, not C, not B, A. There's one more thing we can do. Have a stare at it. Have you spotted it? The first and the last terms have common factors of A and not C, or not CA. So you've got A not C multiplied by not D or D not B. So that's the absorption law again. Get rid of the complemented term in the ANDed variable. That's A not C not D or A not C not B. So not E is equal to, just got rid of those two from the absorption law and replaced them. Not C, not B, A. Cross them off when you've accounted for them. Not D, B, A, or not D, C, not B. And that is not E. So the segment E, when we put it through a NOR gate, that's the expression that we'll use. Now we'll move on to not F, because there's not many cases when F is low, so we'll focus in on those. 2, 3, 4, 5 and 6 states when F is low. Write out the Boolean expressions. I wish I'd crossed them off earlier to make it so much easier to keep count of where I am. Cross that one off. Then not D, not C, BA. Or not D, CBA. Cross that off. Or DC, not B, not A. DC, not B, A. So there's the complement law in the last two. And in the third and fourth, we've got common factors, and we can complement out the value of C, because it doesn't matter whether C is high or low, because both terms are true. So the value of C is redundant from the complement law. Then those two both have DC and not B. So it's the value of A that doesn't matter. So they reduce to DC not B. Then include the other terms that we haven't touched yet. B not A. We're looking for commonalities and differences. So in the first and third terms, we have not D and A as common factors, and we have B or not B, C. B or not B, not C, I should say. So that's the absorption law. Bring out the common factors. That goes into not B, not C, or B. So it's the not B that we need to get rid of, because that's the complement in the ANDed term. Then multiply out. Not D, not CA. I'm just doing it alphabetically if you don't have to. Then not D, B, A. You notice with the absorption law, it's only one of the terms that actually changes, but I still write them out again afterwards to show what I've done. So we've got not D, not C, A, or not D, B, A. Cross those two off, bring the others down that we haven't touched in a while, or D, C, not B. There's more that we can do. The first and third terms now have common factors of not D and not C. And we've got A or not AB, and that is the absorption law again. So we've got not D, not C into literally A or not AB, which is the way that we learn the absorption law. So the not A is the imposter, so we get rid of the not A and then multiply out again. Or not D, not C, B. And then regroup, not D, not C, A, or not D, not C, B, or not D, B, A, or D, C, not B. And that is the minimized expression for segment not F. Put it through a NOR gate, it gives us segment F. Finally, segment G, we're going to use not G because there's not many times when it's low, and this is going to be quite simple. 3 different states. The first 2, you can see we have the complement law anyway, just looking at the truth table values. So the value of A doesn't matter in the first 2 terms, because we have common factors of not D, not C, not B. They're both true, so A has no effect whether it's high or low, and that's what the complement law is about. So that is worth not D, not C, not B, or the other term, the final term, which was not D, C, B, A. And that is the minimized expression. There's nothing else we can do. So we're ready to implement this and make our full hex 7-segment decoder on Proteus. So implementing the full binary to hexadecimal 7-segment display decoder using Proteus, having learned Boolean algebra. So I want to show you something. If you right click a wire and place a wire label, I've done one already, if you put a name in for the wire, then any other wire that you give the same exact name, there'll be a logical connection between those 2 points, saving you from having wires going all over the place, making it a lot more tidy. So I do that a lot in my designs. So now we're going to implement segment A. Now segment not A, the expression that we had 2 4-input AND gates and 2 3-input AND gates. So if we use an OR gate, that'll only give us the output for not segment A. So we put a NOT gate on the end, and that'll give us segment A. But we can combine those 2 into a NOR gate, which I'll do later. And these are the 4 binary expressions that we worked out earlier for the value of not A. So we just wire them up. So the output from the OR will be not segment A, because we worked it out to be not A, equals all that. And after the NOT gate, it becomes segment A. So let's just wire it up the way that we worked it out earlier, using our Boolean simplification. D, not C, B, and A, or D, C, not B, or C and not B and not A. I've placed the Y label, called it A, and I've called the 7-segment segment, I've labelled that as A as well, so they are logically connected. So the OR gate gives us not A, and after the NOT gate, that gives us segment A, ready to wire up. Now segment B, which had a 4-input AND gate and 3 3-input AND gates. I'm going to use a NOR gate instead of the OR and a NOT because it saves us a gate. We don't need the NOT gate now. The expressions for segment B using the NOR gate as shown, DC not A or CB not A, so we just wire those up. Not D, C, not B and A, or D, B, A, or DC not A, or C and B and not A. And that'll give us, with the NOR gate, that'll give us segment B rather than not B. So we wire that straight up, and I've logically wired it using a wire label and calling it B. For segment C, we've got these three ANDed terms going through an OR gate and a NOT gate, or a NOR gate. So that is the output directly to segment C. So let's wire that up. D and C and B, and D and C and not A. Place a wire label, call the segment the same label, and then they're already connected. Same for segment D. Add a wire and a wire label, label it as D, and label the segment D as D as well, and they are connected. Then for segment E, there's our expressions to wire up, and that is the output. We worked out what not E is worth, so once we not that, it tells us what E is, segment E. Not C, not B, A, or not D, C, not B, or not D, B and A. And using the NOR gate, that is segment E, ready to go. Just two more. These just came from the Boolean expressions that we worked out. We just wire them up from the outputs of our counter, which will cycle through all the numbers for us. D, C, not B. And that we need to label, put a wire in and label it as F, then label the segment on the 7-segment display as F as well. And finally G, that was a piece of cake. G, a 4-input and a 3-input AND gate, which are called AND4 and AND_3. So we have not DCBA or not D, not C, not B. Now we're ready to roll and test it, see if it works. You'll notice that as I right-click the labels on the 7-segment display, I've called them the same as what the outputs are for those logic expressions. I've also labelled the clock wire, and I've labelled the outputs of the counter QA, QB, QC and QD, and I've done that at the counter end of course as well. It means that we can just look at the output to simulate without having to see the whole circuit. So I'll simulate 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we've done it. We've fully decoded a 7-segment display using a hexadecimal number system, something that isn't freely available as a chip. So I hope you found this useful in learning Boolean expressions and algebra and using it on Proteus. And thanks so much for watching, and comment with any questions that you have. Thanks a lot.